Welcome to Physics for Life. This is a quick revision video of chapter Nuclei. So, nucleons, protons and neutrons which are present in the nuclei of the atoms are collectively known as nucleons. Atomic number. The number of protons present in the nucleus is called the atomic number and it is denoted by Z. Mass number. The total number of protons and neutrons present in a nucleus is called the mass number of the element and it is denoted by A. So, if n is the number of neutrons in an atom, then its formula is A minus Z, where this Z is the number of protons or electrons, and here this A is the number of nucleons in an atom. Now, next is nuclear mass. So, the total mass of the protons and neutrons present in a nucleus is called the nuclear mass. Next is nuclide. So, a nuclide is a specific nucleus of an atom characterized by its atomic number Z and atomic mass A. It is represented as X, and here A and below the A Z. And here this X is the chemical symbol of the element and Z is the atomic number and A is the mass number. Now next is isotope. So the atoms of an element which have same atomic number but different mass number are called isotopes. Isobars. The atoms of different elements having different atomic number but having the same mass number are called isobars. And one thing, isotopes. The nucleides having the same number of neutrons are called isotones. Now isomers. So these are the nuclei with the same atomic number and same mass number but are different in energy states. Now atomic mass unit or AMU. So it is defined as the 1/12th of the mass of carbon 12 atom. So its value is given as 1 AMU is equals to 1.660565 into 10 to the power minus 27 kg, which is equals to 931 mega electron volt. And 1 electron volt is equals to 1.602 into 10 to the power minus 19 joule, and 1 mega electron volt is equals to 10 to the power 6 electron volt, which is equals to 1.602 into 10 to the power minus 13 joule. And electron volt, it is defined as the energy acquired by an electron when it is accelerated through a potential difference of 1 volt, and it is denoted by EV. Now relationship between the size of nucleus and mass number. So it is found that the radius R of the nucleus is proportional to the cube root of its mass number. So R is equals to R naught A to the power 1 by 3, where this A is equals to 1.2 into 10 to the power minus 15 meter, and that 10 to the power minus 15 meter is 1 Fermi. Now next is nuclear density. So the density of the nucleus is independent of the size of the nucleus and is given as rho nucleus is equals to m nucleus upon 4 by 3 pi r cube, and the nuclear density is of the order 10 to the power 17 kg per meter cube. Now next is discovery of neutrons. So neutrons were discovered by Chadwick in 1932 when beryllium nuclei are found are bombarded by alpha particles. Highly penetrating radiations are emitted, which consists of neutral particles each having mass nearly that of proton. These particles were called neutrons. So helium plus beryllium, we get 1 neutron plus carbon 12. A free neutron decays spontaneously with a half-life of about 1000 seconds into a proton, electron and an antineutrino. This is the equation. Now next is nuclear forces. So these are the strong attractive forces which hold protons and neutrons together in a tiny nucleus. These are short range forces which operate over a very short distance, about 2 to 3 FM from a nucleus. So the nuclear force does not depend on the charge of the nucleus. Now mass defect. So the difference between the rest mass of a nucleus and the sum of the rest masses of its constituent nucleons is called its mass defect, and it is given as delta m, which is equals to ZMP plus A minus Z into Mn minus M. Now binding energy. So it may be defined as the energy required to break up a nucleus into its constituent protons and neutrons and to separate them to such a large distance that they may not interact with each other. So it may be also defined as the surplus energy which the nucleons give up by the virtue of their attractions when they become bound together to form a nucleus. So the binding energy of a nucleus X is given as del EB, which is equals to ZMU plus this is for H, and plus A minus Z into Mn and minus M and bracket close into C square. Now binding energy per nucleon. So it is the average energy required to extract one nucleon from the nucleus. It is obtained by dividing the binding energy of the nucleus by its mass number. So del EB and or B bar will be equals to binding energy per nucleon and this is the mass number, and here this is the binding energy. So it is equals to binding energy upon divided by its mass number. Now packing fraction. So the packing fraction of a nucleus is its mass defect per nucleon. So packing fraction of a nucleus is equals to del m, that is mass defect, upon A, which is mass number. So it is directly related to the availability of nuclear energy and the stability of nucleus. Now next is nuclear energy levels. Like an atom, the nucleus exists in nucleonic configuration which correspond to the nuclear stationary states. The stationary state of the lowest energy is called the ground state, and when a nucleus makes a transition from one level to a level of low energy, then they emit photon belong to gamma ray region of its electromagnetic spectrum. Now next is radioactivity. So it is the phenomenon of spontaneous disintegration of the nucleus of an atom with the emission of one or more radiations like alpha particle, beta particles or gamma rays. So the substances which spontaneously emit these penetrating radiations are called radioactive substances. Now Soddy-Fajan's displacement law. So it states that first, when a radioactive nucleus emits alpha particles, its atomic number decreases by 2 and mass number decreases by 4. Second, when a radioactive nucleus emits beta particle, its atomic number increases by 1 but mass number remains same. Third, the emission of a gamma particle does not change the mass number or the atomic number of the radioactive nucleons. So now alpha decay. So it is the process of emission of an alpha particle from a radioactive nucleus. Here you can see its mass number is decreasing by 4 and atomic number is decreasing by 2. And here an helium atom and some energy. Next is beta decay. So it is the process of emission of an electron or a positron from a radioactive nucleus. So this is of two types. First is beta minus decay and second is beta plus decay. Now next is gamma decay. So it is the process of emission of a gamma ray photon during the radioactive disintegration of a nucleus. This occurs when a nucleus in an excited state makes a transition to a state of lower energy. So this is the excited state and this is the ground state. So now next is radioactive decay law. So the number of atoms of a radioactive sample disintegrating per second at any instant is directly proportional to the number of undecayed radioactive nuclei present at the instant. So here you can see the expression dN upon dt will be equals to minus gamma n. So the law may be expressed as n is equals to n naught e to the power minus lambda t, where this n naught is the number of nuclei at time t is equals to 0 and lambda is the decay constant. Now next is decay constant. So it may be defined as the reciprocal of the time interval in which the number of active nuclei in a given radioactive sample reduces to 36.8% of its initial values. and its units are per second, per day, per year, etc. Now half-life. So the half-life of a radioactive substance is the time in which one half of its initial number of nuclei uh, disintegrates. So here you can see the formula. T half will be equals to 0.693 upon lambda, and n is equals to n naught 1 by 2 to the power small n, where this small n is the number of half-lives in time t is equals to t by t1 by 2, and its units are second, day, year, etc. Now mean life. So it may be defined as the ratio of the combined age of all the atoms to the total number of atoms present in the given sample. So tau will be equals to 1 upon lambda, which is equals to t1 by 2 upon 0.693, which is equals to 1.44 t1 by 2, and its units are second, day, year, etc. Now next is decay rate or activity of a sample. So it is the number of radioactive disintegrations taking place per second in a given sample. So R is equals to modulus dn upon dt, which is equals to lambda times n, which is equals to lambda n naught e to the power minus lambda t, or R is equals to R naught e to the power minus lambda t. Now backward. So it is the SI unit of activity and is defined as the decay rate of one disintegration per second. So 1 becquerel is equals to 1 decay per second. Now Curie. So 1 Curie is the decay rate of 3.7 into 10 to the power 10 disintegrations per second. Here you can see 3.70 into 10 to the power 10 disintegrations per second. Now next is Rutherford. 1 Rutherford is the decay rate of 10 to the power 6 disintegrations per second. Now natural radioactivity. It is the phenomenon of spontaneous emission of alpha, beta or gamma radiations from the nuclei of naturally occurring isotopes. Now artificial or induced radioactivity. So it is the phenomenon of inducing radioactivity in a certain stable nuclei by bombarding them by suitable high energy particles. Now next is nuclear reaction. So it is a reaction which involves the change of a stable nucleus of one element into the nucleus of change of one stable nucleus into the nucleus of another element by bombarding the former with suitable high energy particles. Now next is nuclear fission. So it is the process in which a heavy nucleus of atomic mass greater than 230 when excited gets split up into two smaller nuclei of nearly comparable masses. For an example, uranium 235 plus 1 neutron, then you will get beryllium, here barium 141 and krypton 92 plus 3 neutrons and some energy. So now next is thermal neutrons. So these are the slow moving neutrons of energy 0.0253 electron volt, corresponding to the velocities of 2200 meter per second. Now next is multiplication factor. So the multiplication factor of a fissionable mass is defined as the ratio of the number of neutrons present at the beginning of a particular generation to the number of neutrons present at the beginning of the previous generation. And if k is greater than 1, then the chain reaction grows. If k is equals to 1, then the chain reaction remains steady, and if k is less than 1, then chain reaction gradually dies out. Now next is critical size and critical mass. So the size of the fissionable material for which multiplication factor is unity is called the critical size, and its mass is called critical mass of the material. The chain reaction in this case remains steady or sustained. Now next is moderator. So any substance which is used to slow down fast moving neutrons to thermal energies is called a moderator. The commonly used moderators are water, heavy water, that is D2O, and graphite. Now next is nuclear reactor. So it is a device in which a nuclear chain reaction is initiated, maintained and controlled. The reaction is controlled by using neutron absorbing materials like cadmium rods. Now next is nuclear fusion. So it is the process of fusion of two smaller nuclei into a heavier nucleus with the liberation of a large amount of energy. For an example, two helium atoms get combined to form two hydrogen atoms get combined to form one helium atom, and 24 mega electron volt energy. So these reactions require the extreme conditions of temperature and pressure so that the reacting nuclei can overcome their electrostatic repulsion. For this reason, these reactions are called thermonuclear reactions. Thank you for watching the video.